Welcome back everyone. In this lesson we are going to learn about another open method which is termed the inverse quadratic interpolation method. So in the previous two lessons we have learned about two different open methods which are Newton-Raphson method and the second method. And now we are going to learn about the inverse quadratic interpolation method. Okay, first of all, before diving into the inverse quadratic interpolation method, we are going to see the normal quadratic interpolation method or the QIM method. This QIM or quadratic interpolation method is very much similar to the second method, but there is a slight change in the formula. For example, in the second method, we used two different starting points. Although in the modified second method, we used just one starting point, but now we are just considering the original second method just for comparison. So in the original second method, we used two starting points, but in case of quadratic interpolation method, we are going to use three different starting points. So that's the difference between these two methods. Just for clarification, look at this figure. In this figure we are drawing a function f of x with respect to x, and this function is denoted by the blue line. This blue curve is our original function. So what we are going to do, we are going to assume three different starting points which are denoted by these black dots, this one, and this one. Using these three black dots we are going to fit a parabola within these three dots. So what is going to do, we are going to do with this parabola, we are going to fit a second order polynomial which is also known as the parabola, and that parabola is going to intersect the x-axis at a specific point which is this white dot. So this white dot, the intersection point of the x-axis, is our approximation of the root. So that is the difference between the second method and the quadratic interpolation method. So if you remember carefully that in the Newton-Raphson method, second method or modified second method, we try to fit a straight line through the initial starting points. But now through our initial starting points, since we have 3 points, we can fit a parabola. That means a higher order line. In the case of second method or Newton-Raphson method, we use the second order polynomial, a first order polynomial which is a straight line. But now we are going to use a second order polynomial because we have higher number of points. So that's the difference between the quadratic interpolation method and other open methods. So we are going to dive into the details of this quadratic interpolation method in our next few slides. So there is a slight flaw in the quadratic interpolation method. It might happen that the fitted parabola might not intersect the x-axis at any point. In that case, we will not find any of the root possible. So what we do, we fit not a quadratic interpolation, quadratic interpolating curve. Rather, we fit an inversely quadratic interpolation curve. And it sometimes happens that for the case of complex roots we do not find any kind of parabola intersection, and that's why we use the inverse parabola curve. So what we do in the inverse parabola curve, we do not fit a curve based on the independent variable x. Rather, we fit a curve based on the independent variable of y. That means here the independent variable is y, and so we fit a curve x equal to f of y. So our function is a variable of y. So from the figure it is very prominent. You see the y equal to f of x curve, which is the blue curve, might not intersect the x-axis at some point. So as a result we will not get any of the roots. But if we convert the independent variable from x to y, our curve will be opposite, reversed, and that is the black curve, which is the inverse parabolic curve x equal to f of y, and it will intersect any line at any point which is ensured in this case. As a result, we will always get any root in this case. So no matter where the parabola is, it will always intersect the x-axis. The inverse quadratic line will always intersect the x-axis, and that's what we need. Now let's look at the equation, that is the equation of the parabola that we are going to use through our three initial starting points. Say for example, we are given three initial points, xi minus 2, yi minus 2, xi minus 1, yi minus 1, and xi, yi. These 3 points are initially given. So we are going to fit a parabola through these 3 points. So the Lagrange formula is going to be used. So some of you might hear about the Lagrange formula. If you do not, there is no need to prove this formula. We are going to use this formula, equation 1, as a reference. So there are some patterns in this formula so that you can easily remember the whole equation. For example, in the first, there will be 3 terms. Since we are given 3 separate points, there will be 3 separate terms. And in each of these terms there will be separate patterns. For example, in the first term, the multiplicative term is xi minus 2, and for this case, from the numerator there will be no yi minus 2 terms. Look at this. In the numerator of the first term we have y minus yi minus 1 multiplied by y minus yi. There is no yi minus 2 term. So this is the pattern. Similarly, in the second term, we have the multiplicative term as xi minus 1. So there will be no yi minus 1 term in the numerator. Look at this. There is no yi minus 1 term. Similarly, in the third term, there will be no yi term in the numerator. So that's the pattern that we are going to follow. Now let's look at the denominator. In the first case, our multiplicative term is xi minus 2. So we subtract other y terms, that means yi minus 1 and yi, from the yi minus 2 term. So that's the pattern. We subtract the other y terms from the corresponding yi minus 2 term. Similarly, in the second term, we have the multiplication as xi minus 1. So there will be a subtraction from the yi minus 1 terms. Similarly, in the third case, the subtraction will be from the yi term. So these are the patterns that we are going to follow to memorize or to remember this Lagrange formula. So this whole equation 1 is a Lagrange formula that we are going to use to fit a parabola. Now this parabola is going to intersect at say any of the points in the x-axis, and that intersection, the corresponding y value or the function value would be 0. So if we substitute the function value at that intersection point, that means y equal to 0, then we will get our corresponding root, which is xi plus 1. So substitute y equal to 0 into the first equation and then solve. We will get our approximation root as xi plus 1. So this is our approximation root equation that we are going to use to find the root at any specific iteration. So our algorithm is very much straightforward. We are going to initialize with 3 separate points that are xi minus 1 and xi minus 2. These are the 3 initial starting points. And then in step 2, we are going to use the equation 2 of previous slide. That means our Lagrange interpolating polynomial, something like this, that we are going to use to find out the approximation of the root. So here xi plus 1 is our approximated root. Later, we are going to find out the approximation error from using the approximation of the root from the current iteration and the previous iteration. We already seen this in the previous few slides, few lessons. And then in step 4, we are going to compare the results of results of a percentage relative error with our previously determined error limit, and if the error is less than the error limit, we are going to terminate the calculation. Otherwise, we are going to step 2 and recalculate the whole procedure. So remember, whenever we are using the Lagrange polynomial equation, if we use the quadratic interpolation method, then in the right hand side of the equation, all the our independent variable will be x, but if we are using the inverse quadratic interpolation method, then all the x terms will be replaced by y terms, and vice versa. So that is the caution that we are going to follow. We must be careful about the variables that we are going to use in the equation, whether it is quadratic interpolation method or the inverse quadratic interpolation method, that we have to be care about. So let's look at an example. For example, we are given three separate points: 1, 2, 2, 1, and 4, 5. So we are asked about fitting a quadratic equation in both x and y terms. For the first case, y equal to f of x, which is going to be used for quadratic formula, and for the later case we are going to use x equal to g of y for inverse quadratic interpolation. So for the QIM method, that means quadratic interpolation method, our independent variable will be x, but for the inverse quadratic interpolation method, IQIM method, when our independent variable will be y. So the corresponding Lagrange equations will be different. So for example, if we look at the solutions, the reversing the x and y's in equation 1, we can use the quadratic term in x. That means the equation, Lagrange equation that we saw in the previous slide, it was for the inverse quadratic interpolation method. So to find out the quadratic interpolation method, corresponding Lagrange equation will be written something like this, where all the y terms from that equation will be replaced by x and all the x terms will be replaced by y. So if we substitute all the values, we can get this equation, which is f of x equal to x square minus 4x plus 5. This is a second order polynomial that we initially guessed that we have to fit a second order polynomial, a parabola, within our through our three initial starting points, and that is the equation of the parabola. So once we fit this equation, we can get our solutions by solving this equation, which is very straightforward. X equal to 4 plus minus, which is the formula that we usually use, y equal to minus b plus minus root over b square minus 4ac by 2. That's the equation that we are using. So if we solve this, we are going to get two separate roots, which are 2 plus minus I. These are complex roots. Okay, these are complex roots. Now if you are going to use since all these solutions that we have got using the quadratic interpolation method are complex, that means the parabola y equal to f of x does not intersect the x-axis. So these kind of situations that we were talking about, that we will not get any real root using the quadratic interpolation method. So we have to go for inverse quadratic interpolation method. That means we are going to use the equation of the Lagrange polynomial, which we have seen in a couple of slides before, using the inverse quadratic interpolation method. So once we substitute all the values, remember this is another equation which is written for inverse quadratic interpolation method. This Lagrange equation is written for inverse quadratic interpolation method. So if we must substitute all the values, y terms and x terms, we will get this equation, which is 0.5 y square minus 2.5 y plus 4. So this is the fitted parabola curve that we are going to use for IQIM method. So if you remember the equation 2, we can get the new root approximation as. So if you remember a couple of slides before, we have used the method that the fitted parabola curve will intersect at any point in the x-axis, and at that point the value of the function will be 0. So that's what we are using here, xi plus 1. That means the later equation that we have specified a couple of slides before for the inverse quadratic interpolation method. So this equation, g of y equal to 0.5 y square minus 2.5 y plus 4, this is the fitted parabola curve. And this parabola curve, using this parabolic curve, if we find the root of the function, we are going to get 4. So this is very straightforward. So that's the root of the function xi plus 1 equal to 4. So if you see that using the quadratic interpolation method we do not get any real root, but in case of inverse quadratic interpolation method we are getting a root which is 4. So that's the benefit of using the inverse quadratic interpolation method over the quadratic interpolation method. So let's look at some of the limitations that inverse quadratic interpolation method faces. So one limitation we have already discussed about, which is that the quadratic interpolation method might not find any root at some point. It happens when there are complex roots of a function. So in those cases we are going to use the inverse quadratic interpolation method. Also, the inverse quadratic interpolation method requires that all of the three starting points should be distinct. If any two of the 3 points are similar, then the IQIM method will not follow. So then we have to go for second method. So that is going to be a caution for the programmer or you, that you have to be sure that whenever you are using the IQIM method, all the 3 starting points are different. So that's the condition. So it might happen that whenever you are using the IQIM method, initially all the 3 starting points are different, but whenever you calculate through iterations after iterations, then at some point it might happen that some of the two of the starting points are similar. It might happen after some iterations. So in this case, what we are going to do in our program, we are going to set some criteria that at each iteration we are going to check that all of the 3 starting points are different. If those are different, then we are going to use the IQIM method, and if they are not, then we are going to use the second method. So this facility is going to be incorporated in the program, in the MATLAB program or Python program or whatever. So that is the caution that we are going to follow. So in this lesson we learned about quadratic interpolation method, and which is an extension of the second method. We have also seen that there are some limitations of the QIM method. That's why we are going to use the inverse quadratic interpolation method, also known as the IQIM method. So there are some benefits of IQIM method. Also there are some cautions that we have to follow, that all the 3 points of initial starting points should be distinct, and then that's the condition of IQIM method. So in the inverse quadratic interpolation method gives a much more precise root for our problem, so than the second method or Newton-Raphson method, because we are using more information, we are using more data points to fit the curve, and that's why the IQIM method performs better than the second method or Newton-Raphson method in terms of accuracy. So please try out the MATLAB code that I have attached with this video, both the quadratic interpolation method and inverse quadratic interpolation method, and please try out some of the some more functions, and there are some more functions like sinusoidal functions or trigonometric functions, and look at how the quadratic interpolation methods perform. So and that's all for the QIM method. In the next lesson we are going to find about another root finding method, which is the branch root location method, and it's a hybrid method of finding root. It incorporates some benefits of the open methods and some benefits of the bracketing method. So it's a hybrid method. We are going to learn about this in our next lesson. So till then, thank you so much.